one line of work Percy is involved in is in theoretical machine learning. So one example of this is his work in learning latent variable models and various generative models, which we heard a bit about this morning. And another hat is his work in natural language processing, which he's going to give an overview of that area. In particular, he's done a lot of terrific work in an area known as semantic parsing, and hopefully he'll speak about some of that as well.
All right, thanks, John. And thanks, everyone, for coming. It's always good to be back at Berkeley. It reminds me of my grad school days, except for this building wasn't even here at that time. So this talk is going to be about natural language. So it might be a little bit strange. You might think that why is natural language in the kind of foundations of ML bootcamp? Isn't it just like an application of ML? And I want to hopefully throughout the talk kind of convey to you that language itself is something that's really rich and interesting and worth kind of studying. It's kind of the thing that makes us kind of humans. And also, I think there are, by thinking about it kind of in terms of like, language in its own terms, hopefully we can come up with some kind of key foundational questions. Hopefully we'll get to that a little bit later. But a lot of this talk, just so you're kind of prepared, is kind of really kind of trying to think about language without worrying so much about kind of what techniques you're going to use. So let's start kind of, maybe 60 years ago. So there was this guy named Alan Turing who was actually one of the first to kind of think about language and its relationship to AI. So as you know, it's kind of fitting that Turing was one of the, obviously laid a lot of the theoretical foundations of the field. And he actually had some interesting thoughts. So he was concerned with the question, can machines think? And what he came up with was, as many of you know, is the Turing test, where if a computer can convince a human that it is indeed a human, then the computer is passing the Turing test and we declare some sort of victory. And obviously the Turing test has been criticized quite a lot, and there's all sorts of attempts to build things that pass full of humans. But I do think that there's kind of three important lessons to take away. So the first is that this is kind of what I would call a kind of end-to-end approach, right? It's a kind of objective evaluation. As objective, you can evaluate something like language. It doesn't reference how the task is solved, but it's just an evaluation that any of us can. If you sit in front of a terminal, we can probably perform this evaluation. So you don't have to worry about if you're Bayesian or frequentist or using neural nets or rule-based systems. This is kind of above all that. Another aspect of this is that it's an interactive test. Interactivity is actually kind of one of the themes of the workshop, and just like active learning and passive learning have kind of different characteristics. I think the fact that it's interactive actually makes it a bit more interesting than if the test had been just taking a standardized exam. And third is that Turing's initial inquiry was not about language. It was actually about intelligence and AI. So it's kind of interesting that language is a mechanism that he uses to assess intelligence. And as we go through a talk, hopefully I'll argue that language is not just about the words and how they combine, but it's much more about the kind of the meaning, and that's kind of about the understanding. So this talk is, it's called language understanding, not which I want to distinguish from just natural language processing. Okay, so let's, back in the day, people were very excited about building systems that could understand language. So one of the earliest examples was what is called Shortlu. So this is by Terry Winograd at MIT. He built a system where a human could interact with the computer to move blocks around. And if it can have a dialogue, it can ask questions, it can clarify. The computer can come back and ask clarifying questions and so on. If you look at the dialogue, it's actually of quite complex in certain dimensions. It's conveying a certain sense of understanding. It's end to end. You have to understand what the words are. You have to parse it. You have to actually move. There's no robot moving the blocks around, but it was in a virtual world. But you have to do the planning. So it's really kind of the whole package. And it's kind of interesting that this is I guess over 40 years ago, and it's kind of very unlike the systems that we have today, which are very kind of specific in some sense. But as we know, this stuff, you don't have these systems running around for a reason, and that's because they didn't really scale up. And in fact, Terry Winograd, the next year, he wrote this. He's talked about, people thought that this is really kind of a dead end, all these complex interactions between the components, which were powerful, really just made it hard to kind of manage. So interesting, it was kind of almost a software engineering problem that, at least Terry was facing that prevented, the success of, these methods. So eventually, Terry actually went on to, have a very flourishing career in human-computer action and kind of gave up, working on this. So fast forward a few more decades, we know that in the 90s, something happened across AI, statistics and data kind of came onto the scene, and also with the help of having just the resources, and that really just changed the game kind of completely. And in particular, people no longer were restricted to building kind of dialogues that only worked in a single domain, but they were now parsing sentences on the internet, really long sentences. But there was a catch, and the catch is that they changed the problem. So now the problem becomes not end-to-end understanding, but things like dependency parsing, whereby you try to identify nouns and verbs and try to figure out grammatical relations, which is kind of not the same as actually understanding the sentence. And people also worked on a number of kind of word clustering and word vector methods, which I'll talk about later, which it's kind of gets at some aspects of semantics, but I'll argue that this is also a kind of an incomplete picture. So this is kind of a way to think about the landscape in very crude terms. There's a trade-off here. So on one hand, all the new statistical methods are really good at breadth. They cover all. You can throw at any piece of text and it can do something with it. But it's not very kind of deep. It can't really answer hard questions. And on the other hand, you have these systems back in the 70s and 80s, which were really deep, but they only worked in very limited domains. And of course, the holy grail is to get down here. And we're still trying to figure that out. But at least we have a target. OK, so let me elaborate a little bit more about kind of why this might be interesting to kind of ML researchers. Historically, there's actually been a lot of interaction between the machine learning and natural language processing communities. And I'll give a few examples of this. So in actually the 70s, HMMs were a tool that was developed for kind of speech recognition. It was really, with all the kind of algorithms, it was kind of for the purpose of actually decoding acoustic signals into phonemes or words. And HMMs are kind of one really classic example of a larger class of probabilistic models, which got kind of developed further later. In the early 2000s, conditional random fields were actually something that was developed with a particular sequence tagging application, information extraction, in fact, in mind from the I guess it was published ICML, but it was people were interested in solving NLP problems, and this I think really led to a lot of interest in kind of this whole area of structure prediction, where you're not predicting a single label but an entire structure. Latent Dirichlet allocation was for modeling text, and that led to a whole field of topic modeling. And then more recently, all these more advanced neural net models, not just vanilla feed-forward networks, but ones that can do have recurrence and have memory, were developed in response to the needs of some more challenging tasks like machine translation. So all of these cases are where there's some problem in language, which actually is a really strong driver of developing some of these new techniques. And you could try to think about maybe for natural language understanding, where I think in some sense it's quite open what the right way to kind of think about this. I mean, there are many solutions, many proposals, but I don't think anyone has kind of cracked it on the head. So maybe there's some opportunities to likewise do the same. OK, so any questions? Do normally people take questions during the middle of talk? Yeah, I don't want to just like lecture. So if there's any kind of questions, maybe I'll be happy to take them. I'll probably stop out after every section for questions. Okay, maybe I'll go on. So what I'm going to start by doing is really deep diving into kind of the properties of language. So it takes a while to kind of think about, I mean, we all speak language, but we don't always think about language outside language. So I'm going to start there, and then I'm going to go through a number of paradigms that people have used to develop methods for language, and we'll go from there. So you could start with natural language sentences or utterances. And traditionally, you can kind of think about there's as many layers of analysis that you can do. So there's kind of syntax, which talks about what is grammatical, semantics, what does it mean, and pragmatics is what does it do. And I think a good analogy is programming languages, which may be easier to think about in some ways. Syntax means there's no compiler errors. Semantics means that there's no implementation bugs, and pragmatics means that you implement the right algorithm in loose terms. So here's an example where you have different syntax but the same semantics, and here you have the same syntax but different semantics, which is a good way to cause bugs. And here's an example of good semantics but bad pragmatics. So you can implement a deep neural network to estimate basically a probability of a Bernoulli, but which is going to be correct, but like, why are you doing that? So let's start with kind of the basic units. So the basic unit is a word in some sense, like light. But it's a little bit more complicated than that because there's also multiple words that actually behave as if they were a word, like light bulb. And there's also structure inside a word. Many words kind of have, like lightning has the prefix light, which is makes sense. So in some sense, the word is useful but kind of somewhat arbitrary unit. And if you go to a language like Chinese or Arabic, you see that as even more arbitrary. Words can have multiple meanings. So here's a bunch of sentences that contain the word light. Step into a light, the lamp lights, and the load is not light. And in each of these cases, you can convince yourself that light has a different meaning. And conversely, you can have different words that really have the same meaning. And you can have even sentences that really have the same meaning. And of course, this same meaning is it's really more subtle than that. It's more, you can think about the distance metric between words or sentences. But there's more than just kind of similarity. There's also relations between words. For example, a cat is a mammal. A cat has a tail. So these are is and has relationships. And these are useful when you want to do what is known as entailment, which is kind of, you can think about as logical implication if you want. I'm giving a talk about natural language semantics, entails I am speaking. Okay, so those are kind of maybe just kind of warming up with words. Now, what do you do with words? You can put them together to form sentences. And this is kind of known as, the way to think about this is known as compositional semantics. And there's two distinct ideas here, which I think usually kind of get conflated, but I want to tease them apart. One, I think, which is a really important idea is what I'm referring to as model theory, and think about this as model theory in a sense of logic, is that sentences are not just words which are floating around to be analyzed like we do with like other data. It's sentences kind of refer to the world, right? We talk about the world. It's not like we're just spewing out words. And so if I say the block 2 is blue, that refers to a setting where you have a bunch of blocks and the second block is blue. That's kind of in some sense, the meaning of this sentence is the actual context in which the sentence is kind of true. And the second idea is compositionality, which is that the meaning of the whole is the meaning of the parts. So if you have a really complicated, a longer sentence like the block left of the red block is blue, that's really meaningful because this sub-constituent actually denotes block 2. Right? And this is no more, in some sense, is in machine learning, we're very used to this. It's kind of notions of factorization, which allows you to get few examples and generalize to many more. So this compositionality is basically the term used in the context of language. Okay, so just to give you kind of a taste of why language might be difficult. These are kind of interesting things. So there's quantifiers which often give linguists a lot of headaches with every and some, meaning kind of for all and exist. But it's not exactly quite so simple because you have every non-blue block is next to some blue block. It could be the case that for every non-blue block there is some, which could be different, or it could be the other way where there exists a blue block such that every non-block is next to it. And this is a property of language, which is that the order of quantifiers is not necessarily specified in advance. And you can easily see this. Imagine reading some statements of theorems have this property where you read it and you actually wonder what they're trying to say. So many of you probably have experienced this. Modality is something that has to do with not the concrete world, but possible world. So if you say blue block 2 must be blue, that means no matter which situation we're in, the statement is true. Could be means that at least one of it, there's some setting which it could be true. Beliefs. So we know that Clark Kent and Superman are two expressions that denote the same entity, so they have the same meaning. But so you might think that you can always substitute them, but that's not true because these two sentences are different. So this is kind of a case where belief takes a proposition rather than which depends on the kind of the structure rather than just the meaning of it. Okay, so this was kind of about semantics, which is you have words. What do they mean? Well, they denote some property of the world. I think that's kind of a good way to think about it. And then there's pragmatic. So this is where there's meaning that's not just kind of the literal meaning. So I'll give you two examples. One is called conversational implicature. So if you have two people talking, what on earth happened to the roast beef? And the other guy says, the dog is looking very happy. So, what does this mean? Well, probably the dog ate the roast beef, even though this was not part of the literal semantics of that sentence. And this happens all the time. So, that's people talk about the linguists sometimes call it the pragmatic wastebasket. Anything you can't explain in terms of syntax, well, it's pragmatic. It's some sort of context-dependent effect. And then the other one, which I think is a little bit more subtle but really interesting, is presuppositions. And this is where you have a sentence like, I have stopped eating meat. What does it presuppose? It presupposes that I was once eating meat. And the difference between presupposition and conversational implicature is that even if I negated the sentence, so if I say I have not stopped eating meat, the presupposition still holds. So this is something that actually is very insidious. We don't notice this, but there's often these presuppositions that people use when they're trying to be very persuasive that really are traps to look for. And we can now have a term to talk about it. Yeah.
I mean, it seems that there is distinction here between things which are logical implicants or logical consequences, and things which are completely has to do with the human use of the language, which are not logical. And you're referring here mainly to the things which are not logical consequences, right?
Well, yeah, so the question is whether pragmatics is just all the non-logical stuff and semantics is the logical. I mean, these examples certainly suggest that. I think that's not, there's high correlation with what you said, but that's not, there are examples of pragmatics where, in some sense you can think about, you can only logically stop eating something if you are doing it. So this is also kind of logical. And there are cases where in semantics where, which I'll get to a little bit later, which are also non-logical. Okay, so this gives you kind of a, okay, so pragmatics, semantics, just to reiterate, is what is meant literally, and pragmatics is what is the speaker trying to convey. You can think about it, semantics is a property of the sentence, and pragmatics is a property of the speaker and the sentence in context, if you want. And so this was studied by.
Is there a strong line between the two?
There's not a strong line. Yeah, so it's a good point that this is, as with all kind of categorizations, it's useful to think about, but they're really murky cases. So Paul Grice, who's a philosopher, studied pragmatics and came up with a principle to kind of think about it. And the principle is that language is really a cooperative game between a speaker and a listener, where each speaker and listener has goals, and the actions are talking, and pragmatics has to do with what kind of strategies people use to kind of accomplish their goals. And relating to a point made earlier, implicatures and presuppositions are very kind of soft, context-dependent things, which actually is great if we want to kind of do something statistical, because statistical tools are much better for this stuff than the kind of the logical tools that we have. Okay, so what makes kind of language hard is that things are not always fully specified. And in probability, we like to think about kind of this one currency, which is probabilities. They measure uncertainty. Language, there's several notions here which are useful to point out. So vagueness, ambiguity, and uncertainty. So vagueness is when you do not, as a speaker, you do not specify the full information. So I had a late lunch. There's no question what this sentence means in some sense, but it's not clear what kind of late kind of refers to. It's not like you don't know what the word late means. And ambiguity is when there's, it's not that there's there's like a kind of a smooth interpretation, but there's many possible interpretations. One morning I shot an elephant in my pajamas. Maybe you have one interpretation in your head, and then if you see how he got into my pajamas, I don't know. Maybe your interpretation switched, maybe it didn't, depending on, I guess, if you've seen this before. And this is kind of some sort of multimodality you can think about. And then there's uncertainty, which is the witness was being contumacious, and maybe the model doesn't know what contumacious means. It's not that intrinsically the thing that you're modeling is uncertain, but this is like reflection of an agent's lack of capabilities. Okay, so to summarize a really brief whirlwind, linguistics kind of 101 or semantics 101. We can think about sentences as being analyzed via syntax, which is what's grammatical, semantics, which is what it means. Pragmatics is kind of what is the speaker trying to do. You can talk about relations between words. Words get combined together via compositionality to form kind of larger expressions, and these refer to some property of the world. This is the idea of compositional semantics. And then the challenges are, languages is really kind of, it's sometimes it's can be very crisp, but sometimes it's just kind of very loose, and it's loose in all sorts of different ways. Okay, any questions about kind of what language, how to think about language before I kind of move on? Yeah.
I think that one comment about the last point of ambiguity and vagueness. I think that the main issue, sometimes we say things which are inherently ambiguous, but that's not what NLP is going to figure out. But the interesting part is that to a human it's not ambiguous, but it is very difficult to find the meaning with it. We don't have the tools that humans use very spontaneously.
Yeah, so the comment is that we don't, models don't have the same access to all the information that is required to disambiguate as, humans do. And, part of the problem is that, we are kind of really impoverishing our models. We look at sentences and we expect to understand them, but, humans have all this context, both the, immediate context, but also background knowledge, which I'll say a little bit more later.
Can you example of compositionality?
So compositionality is something like this, where the block left of the red block is blue. So you can understand the full sentence in terms of its parts. So block left of the blue block is block 2. and block 2 is blue. So you can break it up. Yeah. Okay, so let's see. So the next 3 sections are going to be kind of 3 different ways to model semantics, if you will. So the first is distributional semantics. So here's a warm-up. If I have these 3 sentences with blanks, can someone figure out what the missing word is? Shout it out when you're clean. Yes, that's kind of a, we're able to do this. Which means that if you wanted to think about what the word clean means, maybe one way to think about it is kind of the contexts in which it occurs, right? So the key idea is that this idea of meaning is so, how do you get a handle on it? But what do we know? We know where this word occurs and where it is. So maybe we can use that as a surrogate in some sense to figure out what the meaning is. And this actually, this idea, may look kind of like a statistical idea, but it actually has some roots in linguistics. It's called the distributional hypothesis by Harris, where there's this quote by another linguist, Colin Firth, who said, "You know a word by the company it keeps." And notice that this is kind of in very stark contrast to the dominant kind of semantic paradigm of much of the the 20th century or latter half of the 20th century is Chomsky's generative grammar, where you kind of it's kind of you sit in an armchair and you think about all the structures that could possibly exist without looking at data, right? So in some sense, this is kind of a much more machine learning friendly view of how to think about meaning. So here is kind of the general recipe, and I'll give you 2 examples of this. This is like kind of the very basic versions of this idea, is that you look at words that you have, first of all, you have a corpus of just sentences. You look at each word and then the context in which they appear, and you count the number of times word I occurs in context J, and then you do dimensionality reduction, and you call each row here some sort of representation of a word. Okay, that's basically all there is to distributional semantics in a nutshell. Okay, so I'll give you 2 examples of this. So one is latent semantic analysis, which goes back to the early 90s. And the idea here is that the context is the document in which a word occurs. So here's 2 documents. You have these words. Cats appears in doc 1, dogs appears in doc 2, have appears in both, and so on. And you do basically SVD, and that is called latent semantic analysis. And this is can be useful for information retrieval. The idea is now if you have a word in your query word and you're trying to match it in a document, you don't have to have an exact match. You just have to match other words which show up in similar contexts, essentially. Here's another example, which is more recently popular, skip-gram model with negative sampling, aka word2vec. And the idea here is that same idea, you have words, and now the contexts are the words in basically nearby words in the sentence. So here, cats occurs next to and occurs next to cats and dogs, and so on. You can use larger window sizes if you want, but keep it simple. And then you could do SVD if you want, and people have investigated that. But one other way you could do it is you can treat this as a logistic regression. It's not exactly logistic regression, but it's basically binary classification, and you run SGD. So the way you set it up is that you train a model that, given a word in a context, it is trying to predict what is the probability that this is a good combination versus a bad one. And here's a simple logistic form that is used in this model. And then you gather positive examples, which are the words and contexts that actually show up in your data. And the negative examples are where you take those examples and you swap out the context for some random context.
How do you represent the context here?
So the context in this model is just a word. So in this case, contexts are just words. Yeah. Okay, so you have a bunch of positive and negative examples. You run SGD, and that gives you word vectors. And there's more sophisticated versions of this, but this is kind of comparable to what is the state of the art. And there's many other ways you can do this. I'm not going to go through the details, but basically any sort of dimensionality reduction where you take words and you try to reconstruct them, or you take words and try to predict the context, is going to give you something similar. And then you can make these nice kind of plots where here a bunch of words have been plotted in actually I think 50 dimensions, but now reduced to 2 dimensionals for visualization. And you can see that some structure actually emerges. So here's a bunch of country names, except for London, and here's a bunch of days of week, months, and years, pronouns in the accusative case, and so on. So it's definitely learned some structure. And remember, what is driving all of this is basically words that occur in the same contexts or kind of similar contexts are put next to each other. So there's no kind of necessarily so much magic here. Okay, so this is a kind of some structure. What's kind of maybe missing? Does this give you synonyms? That's what you would hope for, because 2 words are similar mean the same thing if they show up in the same context, maybe. But if you look at the nearest neighbors of words like cherish, you see that they're adore, love, admire. These are definitely like very related, but not really synonyms. Tiger is definitely not a synonym of leopard, and lion, and these are in some sense they're co-hyponyms. They're all animals, but they're not synonyms. And also, you actually get the opposite of synonyms, because bad and nice actually show up in a lot of the same contexts, because they're I can say that that paper was bad. You can say that paper was good, and the model wouldn't be able to tell. Okay, so there's definitely things which are all of these things. People talk about semantic similarity, right? But there's actually many different kind of actual notions, all kind of jumbled up here. Okay, so, and let's go back to the issue of context, right? I'll show you 2 examples of different contexts. So what is kind of the effect of context? So here's a simple thought experiment. So suppose that the word Barack Obama, I guess maybe I should update this to like Donald Trump or something. Maybe not. So suppose I have these 2 words that always appear next to each other. This is known as collocation. If I had applied a global context, then I would see that the representation of the word Barack and the representation of Obama would be very, very similar. Because, in fact, they would probably be identical, because they occur in the same context, the same documents. But if I had used a very local context, which is the words immediately around, Barack couldn't be, is very different from Obama, right? Because they definitely don't have the same words to the left and right. In particular, Barack always has the word Obama to the right, and Obama never has Obama to the right, and Obama has Barack to the left, but Barack doesn't have Barack to the left. Okay, so clearly there's different types of even similarity you can get by changing the context. Okay, so summary of distributed semantics. Semantics is basically we think about it as a context of the word or the phrase. You form a word context matrix, you do dimensional reduction, and the nice thing about this is it's really simple. If you want something that kind of is a really kind of crude approximation, this is easy. It's a very machine learning friendly. You get tons of data. You can you can study it. And the context is actually something not to be underestimated, right? It captures all these nuanced information about how a word is used. I think there's really, if you look at kind of the tails of where a word occurs, you actually get pretty interesting information. But there's in some sense, it all boils down to what these contexts are. So this is not a method without a specification of what the context is. And I would say that there's no such thing as kind of pure unsupervised learning, because what kind of representations you're going to get depends on the choice of context, as we saw. And furthermore, I think there's a tendency to immediately think of a word and its context as its surrounding neighbors, but the idea of context should be much more general. The context includes the world and the environment around you. And so here's two examples to think about. So Cynthia sold a bike for $200. The bike sold for $200. So if you look at the word sold and where the bike occurs, well, you know, if you think about just like kind of the context, you know, Cynthia and the bike occur in the same context, but, you know, really they're not really behaving the same way. So, and a word distributional similarity would not be able to kind of capture that. Okay. So, any questions about distributional semantics before I move on? Okay, so let's think about what we can do to solve that last problem. So sold is a word, and if you look at distributional semantics, it can tell you all the contexts in which words sold occurs. And it's very kind of holistic, right? It's a monolithic representation. You don't get any kind of structure about what sold is doing. The idea of frame semantics is to think about, move more towards this idea of like language is talking about what's actually happening in the world. So really when you say the word sold, there is, you know, you should think of basically there's a so something should pop up in your head like a stage, and on the stage there's a commercial transaction where there's a buyer, there's a seller, and goods and the price. So in some sense, you know, this is kind of the idea of frame semantics is that this is kind of what happens. The frame kind of is evoked when the word sold, you know, is said. So, you know, in this case, the frame would be seller Cynthia, goods are bike, and price is 200. And there's two properties of frames. One is that they are, you know, prototypical. So it's not meant to this stage as a cartoon of what's going on in the world. So for example, if you have the word widow, what is this? This is stage. It's, you know, there's a woman who marries one man, and the man dies, and the woman's a widow. So that's kind of the context in which you would, you know, think about when you're thinking widow. But, you know, and it's not, you know, you don't have to handle weird cases where, well, what if, you know, a woman has 3 husbands and 2 died? Is that woman a widow? Well, you know, like, forget it. So, and the other aspect is that, you know, you have these frames, but words kind of do this profiling where they highlight one aspect. So sell highlights the seller, buy highlights the buyer. If you have, you know, a stealing event, rob highlights the person, and steal highlights the good. So it's one frame, but kind of 2 views on that frame. So this kind of gives you a notion that frames are kind of a more canonical representation of kind of what's going on, and words are kind of views onto this canonical representation. I'm going to go over this really quickly. There's basically frames are this idea from, you know, linguistics, and has been developed by people like Marvin Minsky in kind of AI and cognitive science. And in NLP, there's kind of very concrete, you know, data sets and resources that have allowed people to train statistical methods. So the main kind of challenge with frames is that, you know, there are many ways of kind of evoking this frame. So each of these sentences is basically kind of a different view onto this frame. And notice that, you know, just because Cynthia is a subject of sold and bike was a subject of sold, it does not mean that they both go into the same frame. And, you know, if you take, you know, linguistics, you'll learn why. But you know, basically, it gets somewhat complicated. So because of this is kind of, you know, messy, you can think about designing machine learning algorithms for solving this task. This task is known as semantic role labeling. About, you know, 2002, Dan Jarefsky and Dan Gildea came up, basically defined this task. And the task, you know, in very concrete terms, you're given a sequence of words, and you're trying to predict a sequence of basically, you know, arguments to the frames and the frames themselves. So the predicate is basically what the frame is. Okay, so I'm not going to talk about the methods, but, you know, pretend just it's sequence tagging.
Frames are usually verbs.
Frames are usually verbs, but they can also be prepositions, and like in, and they also can be nouns. Like I can say the transaction, and that's a frame. I don't have to say the word sell. Yeah. Okay, so there's a lot of work in this area. I'm not going to have time to go to. there's also kind of, this is more recent in the last 4 years, people have been thinking about kind of a more ambitious representation, which does not only frames, but it recognizes that there's entities like people and location, and it kind of normalizes the fact that Cynthia and she actually are the same person, and you basically kind of get these types of structures where every node here is some sort of word or entity in the sentence, not quite, but basically, and there are kind of relations between these entities. So this is the boy wants. What does the boy want? Wants the event, which is visiting. Who's visiting? The boy is visiting. It's the same boy, actually, who's visiting the city, and the city's name is New York City. Okay, so that's the representation. And again, this is kind of actually a very interesting structure prediction problem where you are taking the sentence and you want to build a graph, right? So it's not just a sequence tagging. It's not even like normal parsing where you're building a tree where the nodes are the words, but this is kind of more, think about more as like machine translation. But the output is a graph.
Like the node that is called want01, it's because you have multiple types of want.
Yeah. So there's multiple word senses, and 01 is the first sense. Okay, so this is a brief overview of frames. They kind of are.
Visit was a frame here.
Visit is visit is a frame. Yeah, want is also a frame.
What is want? Okay.
Yeah. So the idea really is that when you hear a word, it's not just that word in isolation, but there's kind of this constellation of kind of related arguments that you need to kind of grab. And sometimes they're specified in a sentence, and sometimes they're kind of implicit, defaults, sometimes there's from the context. So these frames are helpful because they kind of form of, let's say, chunking where you have these stereotypical situations that you can apply over and over again in different settings. And that's all we're going to say. So far we have distributional semantics and frame semantics, and they both.
Can I ask?
Yeah.
The idea for frames, if I remember correctly, was to be done by hand. And so isn't now a temptation to learn them, to sort of, to.
Yeah, so there's question is, aren't frames normally done by hand? And there's two parts to this. One is the construction of what these frames are and what the arguments are. This has basically always been done by hand. And then there's a second part, which is how do you map sentences to these frames? And that is now automatic. Ideally, you would want to learn these frames automatically from data. People have tried doing that, but it's not like a slam dunk. Okay, so frame semantics, compared to distributional semantics, exposes more structure. It gives you an idea of arguments. It's intrinsically it's about relations between things, which you don't get if you are just you take words and you put them into Rn. But in some sense, frames are maybe harder to work with. There's kind of more prior knowledge that you need. So they're less kind of pure in some sense, from a data perspective, at least. But frames also don't handle everything. So consider these two sentences. Well, Cynthia went to the bike shop yesterday. Cynthia bought the cheapest bike. Frames really don't have a really good story. Yesterday, might be treated as kind of a temporal modifier. Okay, so it's just like hanging out there. But but yesterday is actually something that's in this context means it's the January 26th, right? So that frames would not tell you that. And cheapest is actually some kind of mathematical relationship between all the bikes, and frames also don't tell you that. So I don't know if we're not going to do a coffee break, but in case people need to get up or stretch or something or ask questions.
So yes, it's a question. I mean, so can frames provide a sort of a better notion of context for distributional semantics?
So frames can provide us better context for distributional semantics frames can provide a better prior in some sense, because frames, the existence of frames says, here's kind of what I am looking for. And in some sense, frames are also this intrinsically this kind of n-ary relation. So you think about maybe like a tensor if you want, rather than whereas like word-to-vec is just like a bilexical relations. Yeah.
I'm curious if people think about this at all, but I mean, there was this Frenchman called Jacques Lacan who argued that, and many people believed him, that all this is inherently impossible because every utterance we form carries with it basically all our ancestors and the whole history of humankind. And therefore, it's incredibly complex and impenetrable.
Yeah, so this is very hard. Frames definitely do not capture all the meaning in the sentence. In some sense, there's no substitute for the actual sentence plus its context. It's hard to kind of think about like what you can kind of really forget. Distributional semantics gives you a little bit more, I think, in the spirit of what you're trying to get at. Is
Yes.
It gives you a little bit more information about, at least it's looking at all the data in some sense.
It's looking at all the data, but the point is that it should also look transitively, sort of, at what these contexts mean depends on the context and so on.
Yeah, so the key, I think the first order bit is that the context needs to be sufficiently rich for you to actually understand things. And most of the time we are not kind of, the algorithms don't have enough.
Alternatively, the context could be very limited. Like if I can dream about a program that will mark exams for me, when students write exams, right? But there, I don't have to worry about the richness of context because I know what the context is. Maybe it's an easier task where the context is limited. I know that they're trying to answer the question that I asked them.
Yeah, so let's see, your dreams. Well, in some sense, you're still bringing a lot of context from previous experiences to that dream. Having marked many, many exams, presumably. And that influences and shapes the way that you kind of think about that. Maybe I'll go on. Okay, so the third type of way to think about semantics, which I think is the most rich, but like maybe most heavyweight in some senses, model theoretic semantics. And let's go back to the example where every blue block is next to some blue block. Distribution of semantics could tell you that block is like brick. Frame semantics can tell you that is next to, it takes 2 arguments. But really, the only models theoretic semantics could tell you the difference between this setting where the statement is true and this setting where the statement is false. Right? And so we're kind of asking for a much kind of deeper analysis. And of course, we're going to give up some things along the way, which I'll point out. But the goal is to see how kind of deep we can go down the rabbit hole here. So what I'm going to do is talk about this line of work, which I think Sham alluded to, called executable semantic parsing, which I think is a useful way to think about kind of model theoretic compositional semantics. And the high-level idea is that we're going to think about sentences as mapping to computer programs in some sense. So here's an example. If I have a question like, what is the largest city in Europe by population? And you were tasked with answering this question, what would you do? Well, you would think about, there's a notion of cities, and there's a notion of, there's a Europe here. There's things which are contained in Europe. And if you intersect those with cities, now you get a lot of cities in Europe. If you look at population, which is a binary relation, you can compute the argmax over this set using this binary relation, and if you execute that program, you get something.
What? Oh, I'm sorry. I was thinking Istanbul, but
oh, okay. Okay, that's right. Okay, good. Okay, so you did that. I don't know what happened in
That's
your.
a trick thing. It's also in Asia too, but so that's why I was thinking whether it's in Asia.
Yeah, I got this off of Wikipedia. So.
That sentence appears there.
So, and notice that there is something up here, and there has to be a database. It's not just in understanding this question and answering it, it's not just enough to know what the sentence means, but also you have to be able to act on it and bring your world knowledge to bear. Okay? So this is a way that semantic parsing thinks about the meaning of a sentence is in terms of executable program. So just another example, you can apply it to kind of different types of actions. So if you're building virtual assistant or something, you want to talk to it and remind me to buy milk, this maps to some program, and then it gets added to your calendar. So, and in general, you have sentences which are mapped to some sort of program, and when you execute that program, it produces behavior of some sort. And here is, the context is represented here as some sort of knowledge base.
So are you suggesting that all of language is like this, or are you are restricting to a new to special kind of language?
So for now, think about a restricted set of language which is more logical. I think the deeper we go, then necessarily the shallower. So the narrower the scope is. Yeah. But I'll talk about maybe ways of kind of rescuing this later. So there's a lot of work on semantic parsing that kind of comes out of this compositional semantics tradition. And recently, I think there's been even more interest in the NLP community. So now let's go to the problem of how do you go from sentences to these logical forms? And here the idea of compositionality will come in, and this is one of the things that Richard Montague, this logician, kind of really ironed out for English. And the idea is that the meaning of this should be constructed compositionally from the sentence. So cities, what is that? That's cities. Contained in is contained by, and Europe is Europe. And then you can take parts and you can compose them. So it's almost, if you've seen parse trees before, it's kind of like a parse tree, but instead of identifying things as nouns and verbs and noun phrases, you identify things by its logical form or program. So it's a kind of a much richer representation over text. So this is kind of your textbook example. If it were all of that easy, then I think we would be done. But even for this very simple example, there's so many ways you can say European cities, the cities located in Europe, and it just kind of gets very messy really quickly. And so at this point, if you were trying to build kind of a compositional system, here's Terry Winograd who complained about complexity, he would say, no, that's not going to kind of scale up. So I'm going to kind of, there's many solutions to this, but I'm just going to kind of skip ahead to something that's kind of very recent. And we've heard yesterday Russ give a talk about deep learning and all of its successes in object-oriented machine translation. And we can do kind of the same thing with semantic parsing. So what you can do is you can take the sentence and you can put it into basically a recurrent neural network. And basically, this is a real vector which gets kind of updated as you ingest more words. This vector is a representation of the sentence, which somehow encodes a meaning. And then from here, you're going to run the recurrent neural network forward, and you're going to output pieces of the logical form one by one. Sometimes from a linguistic point of view, this is completely insane because it's not modeling any of the compositional structure, but it turns out to be not bad. So the idea here is that semantic composition, if you look at textbook examples, it's very clean, but language is much messier. So let's try to just close our eyes and try to recover from data. So one thing that is useful to do in this context is that notice that we have blown away all the inductive biases of how things combine compositionally, but we can kind of put them back via what we can call data recombination. And the idea here is it's like data augmentation, where you're trying to build in invariances through the data rather than through the model. So if you have what is the capital of Germany, what countries border France, if you've seen those two sentences, you should expect a system, any reasonable system, to also be able to answer these sentences where you just swap Germany and France. So what you can do is you can, given this training set, you can just create more examples by basically doing recombination of your input and outputs and throw them into the neural network, and it can actually, it improves its ability to understand this compositional structure. Okay. Yeah.
But to train those neural networks, you have to create all these semantic translations by hand on your data.
So, okay, good. So what is involved in doing this? I'm obviously glossing over details, but you can define some simple rules that tell you certain invariances, which is much easier than building the full grammar for parsing full sentences. Just like you can take an image and you can rotate it and shear it and translate it without knowing what the image is.
But you need to know the labels then. Right? So you need to know what is the capital of France.
So the training set gives you these labels. And what you need to do is find basically association between things over here and things over here. And once you have these associations, you can kind of replace them with other things. So I don't want to get too stuck on this. It's not so important, but it's just kind of another thing you can do. Let me actually skip over that since I think I have until 3:30. Okay. I do want to save some time for questions, so I'm going to go a little bit fast. So this idea here behind executable semantic parsing is that language actually is a way to encode a computation, and semantic parsing basically is going to represent sentences or language as programs, which basically are endowed with computation. And how you get there? Well, you can use recurrent neural networks, which combine some of the advantages of kind of, in some sense, distributional semantics, because you have, you're basically mapping sentences to vectors, and then you can kind of still retain some of the logical aspects. So the reason I even bring this up is that I think it's one example of a way to kind of connect the different worlds, right? So distributional similarity could tell you what sentences are related without knowing like what its meaning is. It's just these two are the same. So that is generally it's almost like kind of learning a good distance metric that can be useful for the prediction task, which is actually to answer the question or do whatever you want downstream. Okay, so far, if we had examples of sentences and logical forms or programs, then we could do a number of things, including recurrent neural nets, to learn a prediction system that can do that. But this is not going to really scale up. So while we don't have to design rule-based systems anymore, we have to collect this data. And this data requires some expert to go write down these forms. So it would be much better if we can try to learn from lighter supervision. So maybe just the questions and the answers. And the idea is that you can have many people, Amazon Mechanical Turk workers kind of give you this form of data without understanding kind of logic and linguistics and programming. But now the problem obviously becomes harder because now you don't observe the programs. So I'm going to give you kind of a sketch of how you might be able to learn anyway. And this is kind of just for intuition. So if I saw the sentence, where did Mozart to press? And the answer is Vienna. And don't worry if you don't know what to press means, because I just made it up. What the learning algorithm would do is it's says, okay, well, I don't know what's going on here, but let me generate a bunch of hypotheses of logical forms that could be the meaning. And I'm going to execute each one of them and scratch out the ones that don't get the right answer. And okay, at this point, I still don't know what's going on because this Vienna doesn't tell me all the information I need. So fortunately, you have more than one example in your training set. So you go to another example, you do the same thing, scratch out the ones which are not consistent with the data. And now, if you do this over again, you can get kind of statistics about what's actually going on. So what does Tupras mean? Yeah, it's probably place of death is the most likely. It's not for sure, but it's should be higher likelihood than marriage or birth. Okay, so as I presented this is, there's 3 examples, so you can just enumerate them. But in practice, if you have to search over hundreds and thousands of possibly logical forms until you might get the right one that produces the right answer. Okay, so this is. There's a bunch of things you can do here involving kind of reinforcement learning, some dynamic programming, which I'm not going to talk about, but fundamentally it's kind of a hard search problem. If you like thinking about reinforcement learning, it's reinforcement learning with very kind of sparse rewards. So I'll just give you kind of one concrete example of semantic parsing that we did. This is a data set, a wiki table question. So the data set looks like this. This is one of the examples. You have your database, which is actually a table from Wikipedia. And then you have a question: in what city did Pyotr's last first place finish occur? And the goal is to predict the answer. And the answer does not have to be in the table. It might be in the table, but it might not be in the table. Okay, so does anyone know the answer? You heard it, Bangkok. That should be the right answer. So how does this happen? Well, first you look at the position column. You select the ones which are first. You look at the last one, and then you get the row, and then you go over to the venue. Okay. So this is an example of a question. Remember I said that language encodes this computation. It's basically a sequence of steps that you need to do to compute the answer. Okay, so this is actually kind of quite different from many other forms of question answering that you see. For example, if you just where you have a bunch of documents and you answer a question and you basically do keyword matching on the document to find the answer. That's kind of retrieving the answer, but this is more kind of really trying to understand what's going on in the sentence and computing the answer. Okay, so one point I want to bring up is that once you're if you think about this problem, it kind of departs away from kind of just thinking about, what is the meaning of this sentence? Because you have to know that, venue is, somehow related to what city. So there's actually a lot more going on here than just, having a sentence and kind of connecting the words up. And in some sense, the more I kind of work on these type of problems, the more I realize that it's not really about the language at all. So for example, here's a kind of example. So if I had a question, how long is Percy's talk? Well, it's what would be the program? You can imagine just understanding it as length of Percy's talk or something. But in order to actually answer this, given this Simon's website, you have to do something more like this, where you basically get the header information and then you look at the first thing, and that's a date, and you convert it into a date, and then you look at this thing and you convert it into a date, and then you subtract, right? So in some sense, these type of language understanding problems actually require more than just understanding what the words mean, but also how to act to kind of deliver the answer. So like I said before, I think language understanding is a small fraction of, what is necessary to really understand the sentence. So understand, if you look at understanding, I think it dominates, maybe like 80% of natural language understanding. Okay, so to summarize, there's kind of two ideas, model theory and compositionality. Model theory says sentences refer to something in the world, and compositionality says that if you have a sentence, the meaning can be constructed by interpreting the parts and combining them. And both, I think, get at this idea of factorization. I already talked about how compositionality is kind of a notion of factorization. Model theory is also a form where if you think about the end goal of getting the answer from the question, what basically semantic parsing is doing is it's factorizing understanding what the question means from actually knowing the facts. So I can ask you all sorts of questions which you can perfectly understand. These are called conjectures, but you don't know the answer to. Okay, so there's some interesting kind of challenges here. One is that learning from answers and questions it's pretty difficult because it's this kind of sparse reward learning from with kind of needle in a haystack kind of problem. And these things, to the extent that they work, actually rely on something kind of a bit subtle, which is that when you train these systems, they kind of latch onto easy examples first, and that gives you enough so you learn kind of what maybe how long means, and now you can use that information to tackle harder examples. This thing kind of handles, is critical, but we don't really have a good theoretical foundation way to kind of think about this. And going back to some comments earlier, semantic parsing is in this form is restricted to kind of basically short sentences. Think about kind of user to computer kind of utterances. Even though they kind of understands these utterances very deeply. Whereas distributional semantics, you can run it on the internet and you can get something out of it. So there's a kind of this trade-off, and how do you bridge the gap? And then there's some interesting work recently that says, well, maybe you don't actually need semantic parsing at all. Why don't you just learn one of these end-to-end neural networks that basically replaces everything? And there's been some work on doing that. With kind of some success, but it's kind of the jury is out. I mean, these things are pretty difficult. It's not by far a slam dunk, and these are very hard to kind of get to work. So, but it does have the kind of the appealing aspect that for cases where your sentences don't permit this kind of very crisp logical structure, maybe the neural nets have kind of natural degrade kind of more naturally. Okay, so let's move on. So I think I talked about these three types of semantics. I want to shift gears a little bit and talk about kind of one perspective on language learning that I think is important. We've been kind of exploring it. So I'm basically going to talk about one of our recent projects on interactive language learning. So I guess the starting point is, Wittgenstein said in 1953, famously, that language derives its meaning from use. So we've been talking about natural language semantics. What is the meaning of words and phrases and sentences? And this has been really hard to pin down. We have distributional kind of answers, frame answers, model theoretic answers, but really there's kind of no unified way to think about this. And this is yet a kind of a different but somehow very appealing aspect, which is that meaning is just a function of how it's used in practice. And he came up with this idea of a language game, which takes on many kind of meanings, kind of ironically. But the idea is that language is a tool used by humans in some real world situation to get things done. So children use it kind of to communicate with each other, to build, objects, and it's really kind of about the, communication between humans rather than staring at sentences and trying to figure out how the words combine together. So it's a different perspective, which I think let's explore a little bit. So, we designed this game called ShurLearn in homage to Winograd ShurLu, which is basically ShurLu with some learning. And the idea is that there is a context in which the user has some goal. The user wants to transform this configuration of blocks into this one. But only the computer can perform actions. So the user has to talk to the computer. So the user, being human, knows how to talk. So that's good. But unfortunately, the computer doesn't know language. So that's too bad. So the human's going to say something like, OK, remove the red one. And the computer has no idea what the human said. So it's like, what? And the human can basically give some feedback. Says, OK, this was what I meant. And with that information, the computer can make an update, online update to its parameters, thereby increasing its language learning capabilities, and the user makes progress towards its goal. So it's kind of it's a collaborative game. The goals are that to transform this starting state into this goal state, and language is just kind of takes more of a supporting role as a means to get this goal accomplished. Okay, so that's the setting. Here's actually a demo. You can go to ShurLearn.this URL, and let's try it out. So I can say remove, let's say blue, and didn't understand what I meant because it doesn't know colors. So I can click down to go through all the possibilities and say that's the right one, and let's say remove orange. This is the right one. Remove orange. So hopefully it learned what orange meant. So OK, so it knows what orange means now. Remove orange. So hopefully, I think it interpreted orange as like left orange or something. So let me fix that. So now remove brown and so on. And so over time, you get to more complicated goals where you have to say like add brown to leftmost or something. And then here's the right answer. And then you can kind of go through the different stages, and the goals get harder, and you have to use more and more complicated language. So it's kind of designed as a curriculum so that the user can kind of accomplish increasingly more difficult goals, and while teaching the computer more increasingly difficult language. OK, so this was kind of it's an experiment, right? So it's a setting where you have a model which weights initialized to 0, and you're putting out there, and you're seeing if a human can train this model. Okay, so we did this on Turk. 100 different people trained their own little models. It was really fast. It took about 6 hours. And we ranked the players by basically how good they were, which means how many times did they have to scroll down to find the right answer. And these are kind of 3 of the players that ranked the best. And these are kind of the utterances that they used. So notice that some of them used something that looked more like English, and some of them just actually designed some sort of shorthand notation. So it's interesting because the model doesn't actually come with any preconceived notions of what words mean. It knows exactly how to perform actions and what blocks are, but it doesn't know the association with words. So the humans can teach any language it wants. If you go down the list, here's the average players. You see that there's less consistency between the sentences, which means that it takes longer for the computer to learn. And this person tried to use numbers, which the computer actually doesn't understand because the computer doesn't know about absolute position. So this guy, there's a bit of a miscommunication there, so it took a long time. And then you go down to the worst people. You have people saying like, laugh with me, which doesn't really help. And then this person didn't put spaces between the words, which means that the model wasn't able to generalize between anything at all. So this took a long time. It's basically doing rote learning. So this is kind of fun. Yeah.
Did you pay these people?
Yeah, we paid these people.
Good. You have to accept the work to pay them, no? Mechanical Turk. You have to accept.
Yeah, we I think accepted everyone except for like the really. Yeah. I mean, in some sense, there's no normative standard here. We were happy that they could invent their own language. It was more of an experiment to see how people can kind of teach computer language, I guess. So again, there's no restriction on language. So one person decided to use Polish. I think it's Polish. And another person decided to use Polish notation. You know. And
so the system doesn't recognize like conjugated words.
Yeah, so the system, so for morphologically rich languages like Polish, the system is going to struggle a bit more. So this could be fixed if you use morphology or look at characters.
But that wasn't in the model you...
It was not in the model. So I'm not really going to talk about the model. I can answer questions about it later. So one thing that I want to highlight, which is I think it's interesting about communication, is that I'll just go through the example. Suppose the model saw this one example. I said remove red, and I said this means remove has color red. Okay. So now I say remove cyan. Okay. So what do you think the model should predict? So it doesn't know what any of the colors means.
Remove has color red.
So let's say there's 4 possibilities. So basically, any sort of statistical model is going to favor remove has red, right? Because in some sense, that's the prior. I haven't seen these words before, and I saw remove, and last time remove was like remove has red. So this one, probably means has red too. I don't know. It's like a kind of a shrinkage kind of argument.
But couldn't you think that it's whatever can be applied to red? Also, like maybe remove means red, and red means remove.
It could, but I mean, but in some sense, okay. So cyan, brown, and orange all will be treated similarly because I haven't seen these, and red is going to be different. So if you've seen something, then you probably a statistical model would try to predict it more, which is actually the exact opposite behavior of what I think we would all think. And there's this kind of, there's studies on children language acquisition, this mutual exclusivity idea, which is that if I saw remove cyan, I don't know what it means, but I should be probably sure that it doesn't mean remove red. Because if I had meant remove red, I probably would have said remove red. So there's kind of this extra knowledge that words tend to kind of mean different things. So that was not being captured here. So the model wasn't learning as fast. So we didn't want to basically build this in directly because that would be kind of hard coding something very specific. We can actually use a more kind of, a general principle. And the general principle goes back to kind of, Grice, which is, what is the purpose of language? Language is a game between two people and where there's a kind of a common goal. In most cases, I mean, sometimes there's negotiation and lying, but ignore that. So the way we can model this is that, okay, so the computer says we saw remove cyan. It has to kind of recurse on what did the human mean, and I'm modeling the human as like what should I say so that when the computer heard what I said, will interpret what I said as what I meant. So there's kind of basically you can set up these models. There's Noah Goodman actually at Stanford and Mike Frank have done a lot of work on these kind of recursive, or what is called rational speech models. So when we actually first applied this, it actually didn't improve things at all. So it didn't actually help people kind of scroll down less. And we wondered why this was. Maybe the maybe there was a bug or something. But then we realized that, why should it, right? So the hypothesis here is that it's a collaborative game, and the human is trying to communicate in a way that the computer can understand. And we saw those people who were saying like, laugh with me and things like that. So they're obviously not being collaborative. So the model is in some sense wrong. So what we did was we looked at the top 10 players. And here we did notice a jump in the accuracy. So the conclusion is that the pragmatics actually helps, provided that it's accurate, which means that it helps people who are trying to like play nicely. Okay, so that was just kind of a quick overview of, I think, an aspect of language I think is going to be very important because it's kind of thinking about language in terms of actually a goal. So this has kind of natural connections to reinforcement learning. But also in general, I think it kind of is more, the learning aspect of this is much more kind of fundamental. What I like about this, the downstream goal drives the language learning. Interestingly, both the humans and the computers are learning, adapting at the same time. So it used to be the case that on static data sets, if the computer was wrong, then the data set's not going to adapt or change. But if you're talking to a kind of real human being, if the computer doesn't understand, the human will try to rephrase and change basically the input distribution in response. So it's actually kind of an interesting game where you usually think about adaptivity or interactivity as you might be dealing with an adversary. But here actually, you're dealing with what's the opposite of adversary? Like someone who's on your side, right? So that actually might improve the...
Same thing if I do, I have my tablet and I'm writing and the computer is trying to understand my handwriting. Mm-hmm. So the program is learning my handwriting, but I'm also trying
exactly.
to adapt and write in a way that will be understood by the program.
Yeah, exactly. And this happens also when you do Google search. People have like converged on this Googleese language for getting web pages. So yeah, this adaptation actually happens all the time when any two kind of agents communicate with each other. But so in some sense, this is kind of more like you can think about active learning, but this is more almost like teaching dimension in some sense. The human has the ability to actually give examples that maximize learning. Okay, so another point I'll just make is that you can do things in an online learning fashion, but the way in which this is used is actually quite different from the usual kind of online learning and machine learning, where you're using it to basically speed up training on large data sets. You're taking like passes over millions of examples. This is actually kind of much more kind of intricate, where on an example you have to update in a way that both kind of learns on that example in a kind of one-shot way, but also doesn't forget everything that it's learned before. So that might be kind of interesting to look at. Okay, so I'm just going to kind of wrap up here. So just to summarize, I think the bulk of this talk was about how to think about language semantics. I started with distributional semantics, which is most broadly applicable kind of a base, broad coverage, but it produces these representations which are kind of not really articulated and kind of hard to get a more nuanced, not nuanced, but more kind of crisp meaning out. There's frame semantics, which moves more in the direction of having structured representation, but it's not yet a full kind of representation of the world. It's only the prototypical representations. And model theoretic semantics is you're really trying to sink in and represent the full world, have rich semantics, and do kind of things end to end. And this is a type of semantics that can support things like, question answering and, talking to your phone or whatever. And currently it's kind of narrower in scope because you can't handle the complexity of, all natural language. So a major, opportunity here is to try to think about how to kind of marry, different parts of basically different paradigms here. I should just point out that there's kind of, this is not the full story. Recently, there's been kind of more interest in these kind of end-to-end tasks. With deep learning, you basically, if you can cast anything as kind of input-output pairs, you can kind of try to do something there. So a lot of people have been working on reading comprehension, which is the task of given a passage, in this case from Wikipedia, answer these questions. And there's this data set that we put out earlier this year, and it's in, I guess, the crazy world of 2016, once you put a data set out, people just kind of really, we basically implemented logistic regression and with 51% accuracy, and then several months later, the deep neural models are getting like 82% accuracy. So, and in this case, it's kind of interesting that you can kind of solve these tasks, solve is maybe a strong word, but these systems can work well on these tasks without actually going through the model theoretical route. It's not like it understands what this Wikipedia article is talking about and forming a model of like precipitation, but it's just basically looking at the text, and it's able to kind of get by with fairly shallow kind of understanding in some sense. Another area I want to kind of point out, which is becoming increasingly popular, is dialogue. And this is the problem of not dealing with kind of, basically paragraphs or single utterances, but really about a conversation between two agents. So this is an example from the Ubuntu dialogue corpus where two people are talking about, I guess, disk drives. And one thing that's interesting is that it both involves understanding, which has been mostly the topic of this talk, but also involves generation, which is you have to talk back now, and that opens up quite a bit of interesting complications, because now it's in some sense when you're understanding, you're kind of more constrained by the sentence in front of you, but when you're asked to talk, well, there's tons of things you could say, and the space is much more kind of open-ended. A major challenge here is how do you even evaluate this problem? First of all, if you're actually doing dialogue, it has to be interactive. So now you actually have to have a human in the loop for evaluation. You can build simulators, but that's obviously less realistic. And even if you're doing things on a data set, you're not going to predict the exact words which are coming out of this dialogue. So there's a bunch of interesting work here I'm happy to discuss later. So maybe I'll just finish with kind of two takeaways. So hopefully through this talk, I've given you kind of a richer feeling or appreciation of kind of what is involved in language understanding. Maybe the most kind of important point is that language understanding is not just about the words, but it's really about kind of connecting the words with what is going on in the world. And the second takeaway is that maybe it's productive actually to think about language as about communication, and which intrinsically is kind of interactive. And maybe the right way to kind of have models that learn language isn't to get large amounts of corpora and train these models, but actually set up environments where an agent can actually talk to a human and learn, because certainly that's the way kind of humans learn language. So some kind of broad open questions. I talked about kind of distributional approaches to language representation, and then there's logical representations. And the kind of dichotomy really reflects that language really has both, right? You can use language to talk about mathematics, right? And where you're being very logical, precise, and formal. But you can also use language to like express your feelings and emotions and do things like poetry, which is kind of perhaps not the antithesis of being kind of logical. So, and all of these things like fit together in like one coherent system. And most of the time you're somewhere in between probably. An important question is how to kind of represent, knowledge, context, and memory. Because language understanding, remember, a lot of it is successful because you can, I think an earlier comment is, we can understand language because we have the necessary context. And so just by setting up as a prediction problem where you're given a sentence, you're mapping to some string or structure or whatever, is maybe just not the right the setting because it's intrinsically just impoverished. But now if you say, okay, I have the context, well, what's the context? Well, maybe it's the entire conversation up until now. Maybe it's all the web. And now the problem with context is the context is a large object, and we don't know how to necessarily featureize it, right? If you give me a fixed dimensional vector, I can reduce the dimensionality, I can do some transformations on it, but if you give me like the web, I don't know how to necessarily represent the context. And then finally, I think maybe one of the ways forward is not necessarily to create necessarily better models, but actually to create better kind of settings for a language. And I think interactivity is something that's really interesting and worth kind of pushing forward because as I said before, maybe this would kind of unlock a lot of kind of different, you can make a lot of progress by just giving the right supervision signal to a language learner. Okay, so this is kind of things that hopefully that are interesting to think about, and I'd be happy to take questions. Yeah.